Hello everybody, welcome to my YouTube channel. Today we're going to be going over complex numbers, and we'll also be answering some questions that are asked in IBAA math. And so without further ado, let's get straight into it. So a complex number can be written in the form of a plus bi, where I is the square root of -1. So here, z, it's usually denoted by a z, so it's equal to a plus bi, where both a and b have to be real numbers, and I squared is -1. So always remember that. If you're leaving your answer in the form I squared, you shouldn't, and you should just substitute -1 into that. So we can express complex numbers in the complex plane. And the complex plane is a plane where the y-axis is the imaginary part of a complex number, and the x-axis is the real part, like this. So for example, a complex number a equals 3 plus I can be denoted as being 3 units on the right of the real axis and 1 unit up in the imaginary axis, like this. And we often talk about the modulus, or the absolute value of a complex number. And what that means is the shortest distance from the origin of the complex plane to that complex number. So in the case of a, the modulus of a, using the Pythagorean identity, we can find is the square root of 10, because it's the 3 squared plus 1 squared, and the square root of that will be the square root of 10. In general, the modulus of any complex number can be expressed as the square root of its real part squared plus the coefficient of its imaginary part squared. And there's another property of complex numbers, which is known as the conjugate of a complex number. And the conjugate of a complex number will be the same as its complex number, except the imaginary part will have its sign switched. So if we have a complex number in the form a equals z equals a plus bi, its conjugate will be a minus bi. So the sign here is just changed to the opposite. And there's a theorem, which I'll put a proof of in the description, that states that if f of x is a polynomial with real coefficients, then if z is a complex root of that polynomial, then the conjugate of z will also be a root of that polynomial. Sorry. So for example, we have here the function f of x equals x squared plus 1. And we know that z equals I is a root of this. Then we would know that z equals -I, the conjugate, will also be a root of this. So I've given 2 examples of polynomials here and 2 questions, and if you want to have a go at those, pause the video and I will just go over them now. Alright, so for this question, to find the roots of this equation, we can use completing the square. So what we can do is say x plus 2 squared minus 4 plus 13 equals 0, and then 13 minus 4 is 9. So then we can say x plus 2 squared plus 9 is equal to 0, and we're going to have -9 into the square of x plus 2. So we can take the square root of both sides, and we get plus or minus 3i is equal to x plus 2, and hence x is -2 plus 3i, or -2 minus 3i. So this is the solution to the first question that I put up. Okay, for this question, we're given one of the roots of this cubic, and we're given the root -3 plus 4i as a complex root. So what we can do is we can find the other complex root by just switching the sign of this 4i here. So we're going to say -3 minus 4i is the other root. And we can also write a cubic function as the products of x minus their roots. So what I mean by that is we can say x minus x1 times x minus x2 times x minus x3 is going to be equal to 0, which is also equal to this cubic function. So let's expand. So we know x1 and x2. So what we can do is we can expand these 2 brackets and keep this one not expanded. And what that's going to give us is x squared minus x times x2 minus x times x1 and plus x1 times x2. And now we can just substitute, okay, all of that times x minus x3. And we can now plug in our x2 and x1 into here and there. And what we're going to get is x squared minus x1 is negative 3 plus 4ix minus x1 is, oh, sorry about that. This is going to be a minus, and then negative 3 plus 4ix and plus negative 3 minus 4i, like so. So we have, can expand the minus here, and we'll get plus 3 x plus 4i x plus 3x plus 4ix. Oh, minus. Plus, and here we have a difference of squares, so it's going to be negative 3 squared plus minus negative 4i squared. Negative 4i squared is negative 16, and negative 3 squared is 9. So 9 minus minus 16 is the same as 25. And here we can do a little bit of simplification. We can cancel these out and combine these terms, and we're going to have x squared plus 6x plus 25, and all of this, remember, is multiplied by x minus x3, the third root. Okay, we know that this has to equal the function on top. And the only way we're going to be getting a constant term out of these is through the root and not the variable x. And so if we multiply this by the constant 25, it's going to give us negative 25. So the only way we can have that is if x3 is equal to 1. So there we go, we've discovered our third root, which is 1. Okay, now that we're done with that question, let's move on to how to divide with complex numbers. So most operations such as addition, subtraction, and multiplication are pretty straightforward, as we've seen in the previous sections. However, division can be a bit more tricky. So if you're dividing two complex numbers and you want to write your result in the form of another complex number, what you need to do is you need to multiply the denominator with its conjugate, both the top and the denominator, to not change the value of the fraction. But what that does is it makes the complex number a real number, and suddenly we have a complex number divided by a real number, which can be expressed in the form of a single complex number. So let me show you what I am talking about. So if we multiply both the top and the bottom of this fraction by the conjugate of the bottom of the denominator, what we're going to get is, well, this is the difference of two squares again, so it's going to be 4 minus 5i squared, and the numerator is going to be 2 times 4, so 8 plus 10i plus 12i minus 15. Okay, so I squared again is negative 1, so what we're going to get in the denominator is 16 plus 25, which is 41. So we can rewrite this, and 8 minus 15 of course is negative 7, so we can rewrite this as negative 7 plus 22i divided by 41. And now we can split the denominator, and we can split this fraction into two fractions, and this is going to be negative 7 over 41 plus 22i over 41. And again, so we now have another complex number, let's call it z, and it's a single complex number, and this is your A, and this right here is your B. So a lot of IB questions will give you a fraction of two complex numbers, and it will say express this as A plus BI. And so what you do is you just multiply the bottom, the denominator, by the conjugate complex number, and you simplify after you've expanded everything. And yeah. So I'm going to put two questions on the board, and I want you to pause the video, have a go at those, and then I'll solve them in the video as well. Okay. Alright, so here are the two questions. So I want you to write these in the form z equals a plus bi. So pause the video, have a go at that, and I'll be just going over them now. So first we have negative 3 plus 5i divided by negative 3 plus I. So we want to multiply the top and the bottom by negative 3 minus I. So negative 3 minus I, negative 3 minus I. And on the bottom, you're always going to have a difference of two squares. So what we can write is negative 3 squared minus I squared, and minus I squared is plus 1. So it's going to be 9 plus 1 on the denominator, which is 10. On the numerator, you're going to have to expand the brackets, and that's going to give negative 3 times negative 3. So I'll do it up here. Negative 3 times negative 3 is 9. And then plus 3i minus 15i, and then you're going to have I squared again, so minus 5i squared is the same as plus 5. So overall this is just 14 plus 12i. Okay, so we can just rewrite this as 14 plus 12i divided by 10, or just you have 14 over 10 is 7 over 5, plus 6 over 5i. Okay, so that's the first question. And moving on to the second, it's the same process for all of these types of questions. Multiply the top and the bottom by 5 minus 3i. On the bottom, you're going to have 25 minus 9i squared. 9i squared again is negative 1, so I squared is negative 1. We're going to have 25 plus 9, which is 34. And on the numerator, you're going to have 10 minus 6i plus 25i minus, and that minus becomes a plus because of the I squared, so plus 15. So this becomes 10 plus 15 is 25. Negative 6 plus 25 is negative 19i over 34. And I don't think we can simplify any further here, so we're going to leave this as 25 over 34 minus 19i over 34, like so. So now we're going to do an IB type question about complex numbers, so you should be equipped with all of the knowledge to answer some IB type questions. Alright, here we have the IB style question. So z is a complex number a plus bi, and we have the equation 3z divided by 5 minus z conjugate is equal to I. And if you want to have a go at that, you can pause the video and try that for yourself. And I'll give you a tip: you don't actually have to divide any complex numbers here. You're going to have to use another trick. But I've seen this IB question come up in past papers, so they do like to ask these sort of questions where they give an equation with z and they ask for a and b. So what we're going to do here is we're going to express z as a plus bi and z conjugate as a minus bi. So this will become 3 times a plus bi divided by 5 minus a minus bi. I'm going to put brackets around that, and it's equal to I, right? So what we can do here, we can multiply the denominator across. So this is going to give 3, I'm just going to expand this as well. equals 5i minus a minus bi times I. And we can now expand the brackets on the left, on the right hand side. So this is going to be a 5i minus ai plus bi squared. I squared, of course, -1, so minus ai minus b. And now we can observe that 3b is the coefficient of I on the left-hand side, and 5 minus a is the coefficient of I on the right-hand side. So from this we can deduce that 3b is going to be equal to 5 minus a, and negative b is going to be equal to 3a. So we can also say that b is going to be equal to negative 3a. And from this we can put this into here, and we will have that negative 9a equals 5 minus a. And we can add a to both sides. We get a negative 8a equals 5, and that a equals 5 over negative 8. And then we can just put, we can multiply the numerator by 3, or negative 3, to get 15 over 8 is equal to b. So yeah, there we go. Yes, the answer is pretty straightforward. And now we'll do another IB question that's a bit more difficult in just a second. Okay, so lastly we have this question, which is very nice, and it's basically a 4th degree polynomial, and it's asking for the value of alpha and c. And alpha, okay, so these are 3 of the roots. 3 of the 4 roots are 2 minus 3i, alpha and alpha to the 4th. And we know that, okay, forgot to mention, alpha is a real number. And so 2 of the roots are real, 2 of them are complex. And so we need to find alpha. So we also need to use the sum of the roots and the product of the roots from the roots theorem, which basically says that the product is the constant term divided by the coefficient of the leading degree of x or z, whatever. So we have 13 over 1, which is 13, and the sum is b over a, negative b over a. So here's our b, here's our a, and it's going to be 6 over 1 is the sum. So the sum, also we need to find the 4th root, right? And the 4th root, we can just use the conjugate of the complex root. So the 4th root is 2 plus 3i. And the sum is going to be, it's going to be 2 plus 3i plus 2 minus 3i plus alpha to the 4th. It's also going to equal 6. And so we can get rid of these, and we got 4 plus alpha to the 4th equals 6. And wait, I forgot to give you time, but you can pause now and have a go at that. But so we have alpha plus alpha to the 4th is 2, and we can very quickly realize that 1 plus 1 is 2, so alpha equals 1 is going to be a solution for this. That's good. We've found our alpha, and there will be other solutions to this, of course, but we don't need them because we know that alpha is real, and we can also use the product to get alpha, and this leads to a solution of alpha to the 5th is 1, and so alpha is 1. And of course there's complex solutions to alpha, but we're not concerned with them. So the first part of the question is done, and it's pretty straightforward. So now it asks us to find c, which is the coefficient of the z² term. And for this, also alpha being 1 means that alpha and alpha to the 4th are the same thing, which means that this is going to be a repeated root. And so when we're writing the equation using the a product of the roots, it's going to be one of the roots are going to have to be squared. Okay, we'll get to that in just a bit. But now we want to express this polynomial as z minus the root and the product of all of those for each root. So we want to say, for part B, we want to say z minus, the first root is 2 minus 3i, and then z minus, second root is 2 plus 3i, and now we have a repeated root, both of which are 1, so we want to say z minus 1 squared. So this is going to equal that. And now we can expand, and expanding this we get z squared minus z times 2 plus 3i minus z times 2 minus 3i, and then this squared, so I mean it's a difference of squares, not that squared, so it's going to be plus 4 plus 9, and all of this multiplied by z minus 1 squared. And now we can simplify this by expanding, so this is going to give us negative 2z plus 3zi times negative 1, and then negative 2z plus 3zi. So these two will cancel, and these two will combine to give us negative 4z plus, and this is just 13, and that is z squared. And z minus 1 squared is z squared minus 2z plus 1. And now we have this equaling to whatever's on top. And here we don't have to actually expand the whole thing. What we can do is we're looking for the coefficient of the x squared term. And so we want to know what ways there are to get x squared, or z squared, sorry, z squared from this product. And we can have the product of z squared times 13. We can have the product of 1 and z squared. And we're going to have the product of these two. So that's going to be negative 2 times negative 4, which is going to be 8. 1 times 13, which is 13. And 1 times 1, which is 1. So we're going to add all of those up and get 22z squared. And so our C is equal to 22. And that's the whole question. So this has been a video about Cartesian form complex numbers. I'll also make one about the polar coordinates, like the polar forms. So that's it. So hopefully you've had some good practice watching this video, and you're ready for the complex numbers in your AAHL class. Let me just redo that.